Hi everyone. In this video we're going to talk about what it means for a set of vectors to be a basis of a subspace. And intuitively a basis is just going to be a set of vectors that is somehow representative of a subspace. So let's begin with the definition. A basis for a subspace H of Rn is a 1 linearly independent set, and 2 in H, and 2 it spans H. So a basis has to satisfy these two really important properties. It's a linearly independent spanning set. It's a linearly independent spanning set. So as an example, what is your favorite basis for Rn? Well, there are tons of them. These things aren't unique. But what is called the standard basis is E1, E2, blah, 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 En. Yeah, this is called the standard basis for Rn. For R2, what does the standard basis look like? It's just the set of vectors 1, 0, 0, 1, or those fun familiar vectors I hat and j hat, if you prefer. So again, we'll talk more about what it means to be a basis of Rn in the next video whenever we talk about whenever we loop this back to the invertible matrix theorem. But for now, we will just relegate our discussion to some fun subspaces. All right. So we saw in the last video that we had these two new subspaces. We had the null space and the column space, right? So let's work in those spaces for now. Let A be your favorite matrix. -3, 6, -1, 1, -7, 1, -2, 2, 3, -1, 2, -4, 5, 8, -4. Let's think about how we might go about finding a basis for the column space of A. This might seem strange because all that we know is that a basis is a linearly independent set that spans the space. How do we know that it has a basis, right? So we have a lot more to discuss, but let's see how we can get this without really knowing a whole lot of anything. What is the column space of A? Remember, this is the set of all vectors y that are such that y is equal to ax for some x. So it's the set of all possible outputs, right? It's kind of the range of the linear transformation tx equals ax. It's the set of all possible outputs. And it's also the set of all vectors that are linear combinations of these vectors, right? So it's also the set of all linear combinations of the columns of A. Well, how can we instead define the set of all linear combinations of the columns of A? The set of all linear combinations is a span, right? So we know, let me call these vectors v1, v2, v3, v4, v5. We know that the column space of A has to be the span of that set of vectors v1, v2, v3, v4, v5, right? So no matter what, we know that these 5 vectors must span the column space. What do we need now? So we need to know which of these are linearly independent. Yeah? What's a linearly independent set that also spans? What's a linearly independent set among V1 through V5 that also spans? We need a subset that also spans the column space of A. How can we go about doing this? What I want you to do is compute the row echelon form, or the reduced row echelon form. So take A and compute the reduced row echelon form of A. Pause the video. Make sure you're okay with this. You'll have to do this computation on quizzes and tests and things. But if you're really lazy, you could put it in a calculator. But be sure you're okay with computing the reduced row echelon form of A. Alright, so after performing a minor miracle, you should obtain that, hopefully, unless I've made a mistake, right? That the reduced row echelon form is 1, negative 2, 0, negative 1, 3, 0, 0, 1, 2, negative 2, 0, 0, 0, 0, 0. All right. So we know that the columns of the original matrix span the column space, right? Based on this information, which of those columns are linearly independent? Which of those columns are linearly independent? It's the columns with the pivots, right? We look for pivots now. I know that column 1 has a pivot, and I know that column 3 has a pivot, right? But it's not that these two vectors are our basis, but the vectors in the corresponding matrix. I know that this is the column associated with the vector v1, so I know that this vector and this vector are linearly independent. Yeah? And I know that if I take this sub-collection here, we will still span the space because that's where our pivots are. So all that we have to do is put that in a set. We know that a basis for the column space of A is the set of vectors. Negative 3, 1, 2, negative 1, 2, 5. A basis is just the set of these two vectors. They're certainly linearly independent because they're not a scalar multiple of each other, and they still span the whole space by this computation here. Yeah? Good. Let's do another example. Let's take the same matrix. Take the same matrix. Oops. Let's find the null space of A, given the same matrix. Pause the video, see if you can puzzle this together for yourself. So we remember that the null space of A is equal to the set of all vectors x, such that A times x is equal to 0, right? So we're looking for a basis of all such vectors x, a linearly independent spanning set of all such vectors x, such that ax is equal to 0. Well, let us solve for x here, right? This is now a nice linear equation. Let's solve for x. We know that we're going to take our matrix A, augment with the 0 vector, and perform row reduction. Right? Well, what do you get whenever you row reduce? It's that same reduced row echelon form that we just wrote down on the previous piece of paper. I think it is 1, negative 2, 0, negative 1, 3, 0, 0, 1, 2, negative 2, 0, 0, 0, 0, 0. Augment 0, 0, 0. And then from this, we can construct the set of all vectors x, right? Let's just find all solutions, and then we'll worry about finding a basis in a second. How do we construct all solutions for this system here? Well, again, I know that I have my pivots in the first column and the third column, and all of the other columns have to be free variables, right? So let's suppose that x2 is the variable t. Let's suppose that x4 is the variable s. That's an s, I promise. And let's suppose that x5 is the variable r. And these are our three free variables. And let's write now our vectors x1, x2, x3, x4, x5. Well, what does x1 have to be? x1 has to be 2x2 plus x4 minus 3x5, right? And let's use these labelings here. It's going to be 2 t's plus 1 s plus, that's a t, and that's a plus sign, sorry about that, plus negative 3 r's. I hope that makes sense. And we'll do the same thing. What's x2 equal to? x2 is just 1t and none of the others. x3 is going to be 0 t's minus 2 s's and plus 2 r's. x4 is going to be just 1 s and everything else will be 0. And x5 is going to be 1 r and 0 of the other ones, right? So what do you notice about this? We just made a parametric equation of some hyperplane, right? This isn't a big deal. And we know that t, s, and r are parameters that live in the real line, right? So this is just a nice hyperplane. But really, what is this? I now see that the solution vectors of x are equal to, here's my cat. Come here, kitty. I see that my solution vectors are simply linear combinations of these three vectors, right? Linear combinations of these three vectors. And so what can we say, therefore? We can say that a basis, these three vectors, form a basis for the null space. These three vectors form a basis for the null space of A. So let's write down our basis. It's this vector, 2, 1, 0, 0, 0, 1, 0, negative 2, 1, 0, and negative 3, 0, 2, 0, 1. Yeah? Oops, that ran off the screen there. Sorry about that, guys. So this is my basis. It is a set of just these three vectors. And remember, what are the properties that this set of vectors satisfies? It's a linearly independent set that spans the space. Yeah? It's a linearly independent set that spans the space. Cool. Let's do something else. So here's a note. A basis allows us to represent vectors. So they allow us to represent these vectors in a subspace H. How? We know that a basis will form a linearly independent set that spans H, right? Well, that means that for any vector H, yeah, vectors in H, for any vector in H, I know that I can write it as a linear combination of your basis vectors, right? And this is kind of nice. And given a basis, why do we have a unique representation? Why do we have a unique representation? That comes from the linear independence. That comes from the linear independence. And as another note, we know that the pivot columns of a matrix A form a basis for the column space of A. And we've also seen this as well. So that's kind of interesting. All right, so let's go back and talk about this unique representation idea. So this is whenever we talked in class about tiling a plane, right? So suppose you have a nice plane and you want to tile it instead with these funny parallelograms. I hope you all remember this idea. And this coordinate here, this point here has coordinate given by 2 of these vectors plus 1 of these vectors. So with respect to this basis, right, it's a linearly independent set that spans R2. These 2 lines form a basis. With respect to this basis, this point, therefore, this vector from the origin, has coordinate 2 of these guys and then 1 of these other vectors. Yeah? So, and we can do this in general. Let H be a subspace of Rn. And suppose it has a basis B1 through BP. What does it mean if we have a basis here? That means that if we have a vector x and h, remember this set of vectors is a linearly independent set that spans h. Well, given a vector in x and h, I know that there exists a set of constants, C1 through CP, such that x is equal to C1B1 plus all the way down to CPBP. Yeah? And we say the coordinate, we'll call this, the coordinate with respect to the basis is, and we're going to notate this as x with a beta, where maybe this basis has name beta. Yeah, suppose this basis, this set of vectors has a name beta. We have x sub beta, this is the coordinate of x with respect to the basis beta, is given by the vector of those constants, C1 through CP. Yeah? And indeed, what did we have in this little example here? If this was our vector B1, if this was our vector B2, then I know that this point here is 2 B1s plus B2. Yeah? And indeed, what was the coordinate of this point here with respect to the basis? It was 2, 1. Let's do an example. Let H be the subspace of Rn, well, of R3, I guess, with basis given by beta is the set of vectors 1, 2, 3, 4, 5, 6. Well, first, I've now written a set of vectors and I've claimed it's a basis. Yeah? I've claimed that this that H is a subspace with basis given by these 2 vectors. Let's first make sure that it is a basis. Well, they span by hypothesis, but what else could we check to make sure it's a basis? They have to be linearly independent, right? And remember, if we have just two vectors, they're linearly independent if one is not a scalar multiple of the other. If they were scalar multiples of each other, we would have to have this vector be 4 times this vector for the first entries to match up, but that's certainly not true for the second and third entries. So they are going to be linearly independent. So my first question is the vector x equals to -2, -1, 0 in the subspace H. Is this vector in the subspace? If it is in the subspace, find its coordinate with respect to the basis beta. Yeah? Pause the video, see if you can figure this out. All right, so if it is in H, then I need to find the coordinate. But first and foremost, let's see if it's in H. How do we do that? Well, if it's in H, I know that x must be a linear combination of these two vectors, right? So that means that I really want to solve a matrix equation. 1, 2, 3, 4, 5, 6, augment -2, -1, 0, right? And I want to solve this because now I want to find constants C1 and C2 such that 1, 2, 3 times C1 plus 4, 5, 6 times C2 gives you the vector x. Whenever you row reduce, and I hope that you're okay with the steps, if not, let me know, you should hopefully get 1, 0, 0, 1, 0, 0, augment 2, -1, 0. Okay? So, is x in H? Yes, because we have now found the numbers such that this vector times 2 plus this vector times -1 gives you the vector that we wanted, right? We've now solved the equation. But more than that, what do we have? What are the two numbers 2, -1? Those are our coordinates. So this strategy also gets us the coordinates for free. We know that the vector x with respect to the beta basis has coordinate given by 2, -1. So that's kind of nice. And how do we check that? 2 times 1 minus 4 is -2. 2 times 2, which is 4, minus 5 is -1. 2 times 3 is 6, minus 6 is 0. Yeah, so it does work out. Cool. All right. So what type of space is H? We know that it has a basis given by these two vectors, right? It has a basis given by these two vectors. What is it? What does it look like? I know it's in R3 and has a basis with two linearly independent vectors. What does it look like? It looks like a plane, right? It looks like a plane. It's kind of like we have a sheet of paper tilted into the plane, and then here are my two basis vectors, if you can kind of imagine with me there. But it's not really R2, but it kind of looks like it, right? It's a plane. It's a plane, but it's kind of like R2 that's been kind of shifted inward a little bit, right? So it's not R2, but it looks like it. And it's kind of like, again, R2 kind of shifted around or maybe rotated a little bit, right? But it's a plane, and that's exactly what our intuition of a plane is. And how do we know what this looks like is? How do we know what it looks like? How do we make that more defined? Let's consider a mapping. Let's consider a mapping that takes the vector x and sends it to its coordinate in the beta basis, yeah? And suppose that this is a map. Well, what is it a map from? For any vector x that lives in H, yeah? It's going to send it to its coordinate with respect to the beta basis. And how many, or what are the size? What's the size of the coordinates in the beta basis? There are 2 entries there, right? Because there are only 2 possible vectors. So really, this mapping takes H and sends it to R2. Yeah. And because we have uniqueness, remember that linear independence gave us uniqueness of the coordinates, this mapping also goes backwards. So this is a bijection. This is a bijection. And that's kind of interesting. So in general, if we have a basis, beta is B1 through BP, for some subspace H, then we know by a similar argument that the mapping from X to its coordinate with respect to the beta basis is a bijection. So it's a one-to-one onto mapping, or an injective and surjective mapping if you prefer. And so what does H look like? It looks like R. Oops. Well, how many vectors are there? It looks like RP. Yeah. So in this case, it would be RP that's been shifted around, or not shifted, but rotated around or tilted in some way. Yeah. Alright guys, so that's all that I have to say for this video. In the next video, we're going to talk about what it means for dimension. What does it mean for a subspace to have dimension? And then we'll tie all this stuff back to what does it mean, or how does this relate to our notion of invertible matrices, right? So if you have any questions, feel free to reach out to me via email. I'm happy to help, or we can set up a time to Zoom. Thanks so much.